So our first target for today is 4.3. We need to distinguish between exothermic and endothermic reactions and be able to explain whether a reaction, if given a situation, is exothermic or endothermic. We begin with a video that I like to affectionately call Death of a Gummy Bear. Hi, I'm a gummy
If we
bear.
combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product-favored.
Did you see the guts coming out of there? Basically, this is a reaction that involves a hydrocarbon. Gummy bear is a hydrocarbon. Now that molten liquid is a melted version of potassium chlorate, and it is a rich, rich source of oxygen. A hydrocarbon plus a ton of oxygen, yeah, baby, energy is released. Carbon dioxide and water. Now, it wasn't as simple as that, so there will be another thing released, and that's potassium chloride. Ryan.
Was that just a gummy bear in boiling water?
No, it wasn't boiling water. It was melted potassium chlorate.
Oh, okay.
Melted potassium chlorate, which is a rich source of oxygen. Basically, we recreated what happens in every one of your cells every day in teeny tiny amounts, because usually you don't burn a whole gummy bear in one sitting. But as you can imagine, the gummy bear is broken down into bits and pieces and stored in your cells, and then your cells have a ready supply of oxygen. Bam! Energy is released. So the gummy bear and the potassium chlorate is your reactants. Carbon dioxide, water, and potassium chloride are your products. So energy is released. In this case, we call it exothermic reaction. I like to remember it this way. Insects have the skeleton outside. They have an exoskeleton. So we have our skeleton inside. We have an endoskeleton. So when the energy is released to the outside, it is an exothermic reaction. Now, what you're about to see is really, really bad music, but it's really cool because you get to see someone throw a chunk of sodium into a river. A nice mushroom cloud, wasn't it? Okay. Actually, what you saw were two different reactions, both giving off energy. The first reaction was actually kind of weak. That was sodium reacting with water to produce hydrogen gas. Okay? What the explosion you saw was the hydrogen gas igniting with oxygen in the air to produce water. And that gave off a whole lot more energy. Okay? Either reaction gave off a lot of energy. I call this the barking dog demonstration. Let's see if you can tell me why.
The glass cylinders are covered with pieces of filter paper. A solution of white phosphorus dissolved in carbon disulfide is dripped onto the filter paper. Watch and listen, focusing your attention on both the paper and the cylinders.
What's the longer graduated cylinder going to sound like? Higher or lower? So you did learn something from that silly lab. And the longest? A little anticlimactic. Okay, look on number 1 of worksheet 4.1. And the first thing I ask you to do is to give me energy conversions for those situations. So let's practice that with this demonstration. What energy type does this demonstration begin with? Chemical. Very good. Okay, so it begins with the energy trapped in the chemicals that are placed in there and allowed to react. What is it converted into? There is definitely evidence for heat. There is evidence for, we call it electromagnetic, so, or EM. So heat, chemical to heat and light. What else? Sound. Chemical to heat, light, and sound. So those are the kinds of things I'm expecting, Morgan, for number 1. I want you to go from this type of energy to this, and you could have multiple types. Multiple types. Okay, now, here's a different type of reaction. You've got this beaker with a white solid, and this beaker down here with a white solid. He is going to place a puddle of water on this block, and then he's going to mix the 2 white solids together. A gas is going to form, it's going to get really liquidy, and the white solids will eventually disappear.
Barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix these together, and hopefully we should see an endothermic reaction. So what I'm going to do to show how exothermic is, how much heat this is taking in, so I'm going to make this wooden block wet. Okay. Now you will see why I've done that in a second. So I'm going to mix these 2 things together. I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's just worked.
I don't think he's
it's getting
from
cold
around
enough.
here.
Well, you know I've got water on base there.
British.
Yeah.
Fingers crossed. It's actually frozen until, well, we know it's below what? 0. So,
Freezes at 10.
this thermometer is calibrated to -10. It's shot down to -5 by about.
Okay, so what happened? Alec? It took in energy. Actually, did you notice that the sides of the beaker were frosty? So any moisture around the beaker condensed and actually froze because it lost energy to the reaction. So here's an example of a reaction that requires energy to go in. Energy to go in. Cold pack. How does a cold pack work? Usually you have to break something, right? You have to kind of break it. Guess what happens when you break? It's usually it's a cold pack, which is a misnomer, a misnaming. It is a cold pack. Usually you have 2 different chemicals that are in the cold pack, and you have to break them open so that they can mix. What happens, Phoebe?
The chemicals mix and they take energy from the surrounding area.
Let me submit something to you that's very important for you to remember. There is no such thing as cold. Exactly. Heat is something that can be measured. Cold cannot be measured. You can only feel 2 things. Heat leaving your body, in which case you have been programmed by your family to say, ooh, that's cold. No. All your body is telling you is that heat is leaving your body. There is no such thing as cold. Or you can sense heat entering your body, in which case you've been programmed correctly by saying, ooh, it's hot. Okay? So from now on, I don't want you to be like Clinton. Okay? I want you to be Oak Ridge students. So the next time it's 20 degrees F outside, and you feel like you're going to freeze, I want you to go, ooh, there's not as much heat in this air today. That would be scientifically accurate. Let Clinton say, ooh, it's cold out here. We in Oak Ridge say, ooh, there's not as much heat in here. Why do these things work? Because if you've got a swelling, if your tissue has swollen, it is full of blood. And we need to get the blood away from that area, so we put that cold pack on there, and the heat from your skin goes into the cold pack. Everything constricts. Remember, volume gets smaller when the temperature goes down, so everything constricts, and basically the blood comes will tend to move away from that area and bring down the swelling. Yes, Ryan?
How come they tell you can't put like a cold pack on for more than 20 minutes?
Because it's natural for that blood to be there. You don't want too much, because that blood is bringing nutrients to help repair the damage. But if it brings too much of it at one time, then you could get some tissue damage. So you're trying to reduce the tissue, you're trying to strike a balance. You're trying to give your body a little more time to repair the damage. I call this death of Larry, the cucumber.
A pickle is incorporated into a simple electrical circuit.
Oh, Bob, I've been
The forks provide contact between the pickle and the power source.
Bob, oh, it hurts, it hurts.
Alternating current will be passed through the circuit.
Oh, help me, Bob. No more silly songs with Larry. That was his last song. Is it endo or exo? I'm calling it endo, though it is debatable. In order for the reaction to continue, what must you be continuously doing? Putting energy in. What is actually happening, there, you can say there is also a reaction happening simultaneously, and that is the combustion of Larry. But as far as the electrocution of Larry, that is an endothermic reaction. That is an endothermic reaction. So, sometimes energy must be added continuously. In that case, what you have is an endothermic reaction. If the reaction cannot occur without you adding energy, it's an endothermic reaction. Endothermic reaction. Where does the energy come from? The environment. Anywhere. It doesn't care where it gets the energy. Yes?
So, you had a reaction and you just put in a certain amount of energy and the reaction happened. Would it still be endothermic even though you're not continuously putting energy?
It would stop at a certain point. I mean, yes, it would be endothermic, but you stop it by not giving it the energy that it needs to completely react.
So just the reaction itself is what would be endothermic?
Right.
Okay.
4.4 and 4.5. I can explain how activation energy relates to a chemical reaction, and I can identify all the different parts of an energy diagram. We're going to be working on the back of your worksheet. You're going to want to record these two diagrams. They're the key to this section. See anybody here with a first name that begins with R? Ryan. And your middle name is Peter, isn't it? It is now. Ryan Peter. Ryan Peter. Ryan works at the Cheesecake Factory at Westtown Mall. He's a waiter. So if you on weekends you can go, and on Saturday evenings go have him wait on you. If you can afford Cheesecake Factory. Okay? Now, so Ryan on Saturday nights goes there maybe with $20 in his pocket. In order to get there, what is he going to have to do?
Drive?
He's going to have to drive, and if he has to drive, what is he going to have to give up?
Gas.
A little bit of his money. So he has to give up a little bit of his money. So this is him, and this is him using up some of his money, but on an end result, you see, when he goes to work, he likes to be called Ryan. When he comes from work, he wants to be called Peter. I don't know, but that's Ryan. He's a little strange. Okay, so in order to get to the mall, he has to use up some money. But on the average, every Saturday, he makes about $10. So he went to the mall, or at least maybe $15. Let's say $15 because he spent $5 just to get to the mall. He went to the mall with $20. He leaves the mall as Peter with $30. So he made money, right? Made money. In the second situation, he is not working, but he wants to go to the mall anyway, because there is a game store there. FYE. You want to go to FYE. So, that record store, it's also game store and lots of Doctor Who stuff. I know you probably want to get the Doctor Who stuff. All right. So he goes there with $20. He comes back with $10. What did he obviously do at the mall? Lost money. Lost money. Okay, this illustrates both types of reactions. Here, the reactants, you have to give it enough energy to get it going. You have to get it to the mall. It doesn't matter whether he's working at the Cheesecake Factory or not, because if he doesn't get to the mall, nothing happens. And in order to get to the mall, you have to invest a little bit of energy. Right? So and this is why I really, I submit to you, it is not a wise thing to get a job at the mall unless you're a manager somewhere and you're making lots of money. Because if you're going to live in Oak Ridge, it's going to cost you. Same thing with driving over to UT and back. You know, my daughter did it, but it cost her a lot of gas money to get to UT. All right, so in an endothermic reaction, reactants need a little bit of energy to get it going, but when they become products, they actually come away with more energy than they did originally because they absorb energy. They absorb energy. Now, in this situation, Ryan invests a little bit of money to go to the mall, to become Peter, but now he has less energy. Less energy. 10 joules of energy. Where did it go? Went out somewhere into the environment. He lost energy. This is exothermic. Exothermic energy. I need to turn off the touch sensor on my screen. It turns itself on. I don't know why. I don't turn it on. I don't want a touch screen. It turns itself on. All right. So, what kind of reaction is this? Reactants, Ryan has more energy to begin with than he does afterwards. Exothermic. What about this one where Ryan has this much energy and now he has this much energy? Endothermic. What do we call the energy required just to get Ryan to the mall? Lenoir. What? Activation energy. Good job. Activation energy. The energy required just to get a reaction going is the activation energy. What are some examples? You can look at a match and go, ooh, this could potentially catch on fire. And you can stare at it and stare at it and stare at it. Take it to bed with you and stare at it while you're in bed. Take it into the bathroom and stare at it. Nothing is going to happen. What is necessary for these reactants who desperately want to react with one another? You're going to have to give it some energy. You're going to have to give it some energy. Okay? How about this one? You've got a car, brand new car, perfect condition, totally gassed up. The only problem is they forgot to put spark plugs in there. What happens when you turn the key? It's not going to work. It is brand new, fully loaded with gas. Yes, sir. Oh, no, I don't know that much about diesel. Lighting a piece of paper. Do you know that every piece of paper that you deal with could potentially combust? But what does it need? Activation energy. Who are the Boy Scouts here? Any Boy Scouts? So you've learned, how do you produce, can you create activation energy without any fancy, like a lighter or anything in Boy Scout school? How do you do that? With a magnifying glass? Steel wool? That's an energy source. I don't know if that works. Friction? Okay, so Boy Scouts learn to produce activation energy. All right, so I want you to watch this video first. Tell me what you think.
Hydrogen peroxide.
Okay.
You probably have this in the medicine cabinet at home, right?
Absolutely.
What do you do with it?
Put it into cut.
Yeah.
You know, clean things off. Right?
Doesn't really work that effectively for killing bacteria and cleaning out cuts.
Oh.
Actually, check out our
Right.
Facebook page. I put a posting up there about how it doesn't work that well.
Yeah.
But one of the things it does do, here, I have a hunk of raw liver. If you could just go ahead and hold that.
Thanks, Carl.
Your body as a part, I know, isn't that cool?
Yeah.
Your body as a part of metabolism actually generates hydrogen peroxide in its cells.
Okay.
And it's very strong oxidizer. You want to get rid of that hydrogen peroxide. There's something called catalase. It's an enzyme in your body that will break down the hydrogen peroxide into water and oxygen gas. So beef liver actually has catalase in it, and when you squirt the hydrogen peroxide on, just like on a cut, I assumed you didn't want us to like cut you or anything to show how this works, right? It generates oxygen gas, okay? And you know, it looks really impressive, like it's doing something, but again, it's kind of a myth that it actually kills any sort of bacteria or cleans the wound out.
Oh, good to know.
But you can do something really cool with this. You can drop the liver now. We're done with that.
Okay.
So what I brought with me is 35% hydrogen peroxide. This is 10 times stronger than what you have at home, hence the gloves and the glasses. You don't want to get this on your skin.
Okay.
And it gives off oxygen gas if you give it a catalyst, like catalase, or I brought a different catalyst with me. Now it's really cool because it can generate enormous amounts of oxygen gas. So we're going to trap that oxygen gas in some soap, okay?
Okay.
Do a nice little squirt of soap in yours, I'll do one in mine. And what we're going to do is simply pour a catalyst into this container of hydrogen peroxide. We'll break down the hydrogen peroxide into water and oxygen gas.
Now, a catalyst is not going to in any way affect the reaction. Hydrogen peroxide normally breaks down into water and oxygen. It just does it very slowly. So a catalyst is not a reactant and it's not a product. All it does is, well, I can describe it, but it's best to see it.
Now, since we have soap inside here, we're hoping for something
Is this going to explode?
kind of dramatic here. I don't know. And you know what? Go ahead and hold this.
Do I need to step back here,
No,
Carl?
no, stay right where you are, but let me do mine first. Let's
Okay.
do a little test here. See what mine looks like, and then you can try yours. So that's the technique. Just dump it right in and see what happens.
Oh, wow. Okay.
Okay, so
Whoa.
releasing lots and lots of oxygen gas. Okay? So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more of a funnel. And you just generate tons and tons of oxygen. It's being trapped by the soap.
Wow,
Okay? It's like a
okay.
supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will?
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff that might be in a wound. But in terms of killing the bacteria, it's not really all that effective.
Sure.
But it is. If you stick your hand over that, you can feel it's giving off some
heat. Yeah.
It's an exothermic reaction, so it gives off a lot of heat when it breaks down, and it's just really cool.
So where would you see something like this concentrated?
If you wanted to be a peroxide blonde, we could add some to your hair.
Okay.
That's where you get that term from. It's used for bleaching wood pulp to make white paper. It's a little bit more environmentally friendly than bleach.
Okay. So normally it produces oxygen. What you saw was it produced a lot of oxygen. And that oxygen is what created the foam. Okay? Why did it produce a lot of oxygen? Well, it normally does so. But why did it happen so fast? Because of catalysts. How much energy you need depends on each specific type of reaction. Every reaction, my friends, is going to have a different activation energy hill. Sometimes that hill is small, sometimes that hill is very tall. The taller it is, the slower the reaction typically is. Why? Because you have to give it a lot of energy for those molecules to be colliding just the right way. In this case, the hydrogen peroxide has to collide with another hydrogen peroxide, but it has to collide in the right way. So if you have 10 collisions and maybe one will work, well, you're going to have to get them to collide a whole lot more than that. So, if you can get the reactants to collide more efficiently, to react more efficiently, then you need less activation energy. Catalysts help reactants react more efficiently. They help them collide more easily. Not just collide, but collide the right way more easily. And because of that, the reactions can occur quicker because you don't need as much activation energy. So, what will they do to the activation energy hill? If that's the activation energy hill, what will it do to it? Esther? Yes. So now, with a catalyst, that's the new activation energy hill. You don't need as much energy. Now, something I did not emphasize a lot yesterday, remember, the heat of the reaction will always be the difference between the reactants and the products. The difference between that. So all you really care about is how much money you have in the wallet before and how much money you have in the wallet afterwards. You don't care about how much it took you to get to the mall, or how much money you made, how much money you spent when you went out to lunch. All you care about is before and afterwards. Okay? Does that help you complete the homework? All right. All right, finally, can you explain heat flow, temperature, and how a thermometer works? What is the difference between hot tea and iced tea? Now be careful. What is the difference between hot tea and iced tea?
Maybe.
Alice?
Hot tea is hot, and then iced tea has like less heat.
Yes! Good job! Iced tea has a lot of heat. I'm sorry, hot tea has more heat than iced tea. Period. That's all you can really say. Hot tea has more heat than iced tea.
So if we say it's like iced tea's colder, that's wrong?
That's right.
Okay.
So the next time you go to the restaurant, you look at them and say, hey, I would like to have some tea that is significantly has less energy than your hottest tea.
But why is your tea dumb?
They're really hard. I know the words that okay, so like what?
All right.
Heat, or thermal energy, is associated with the motions of atoms and molecules in a substance. The more rapid these...
Okay, So, what are we giving this block of metal? Only if it turns, we're giving it heat. So now this block of metal has heat in it.
Atomic scale motions, the greater a substance's thermal energy, and the hotter it is. When we plunge a hot metal bar into cool water, thermal energy from the bar transfers to the water. While the atoms and molecules of the bar slow down, those of the water speed up. The transfer of energy can be measured as a rise in water temperature.
Okay, now here's an important question. A few seconds ago, Max, that piece of metal was scalding hot. Should you reach in there and grab it now?
No. Oh, no. Well, the water temperature is 35.
Yes. Should you reach out and grab it now?
Sure.
He's right. I mean, you're 38, 37, 38. The water temperature is 35. But wait a second. Max, that was really, really hot a few seconds ago. That was probably several hundreds of degrees hot. And you're saying it's okay just to reach in there and grab it? Yeah. He's right.
How long did you leave it in there?
I mean, right now, you saw it. It's that simple. It's that simple. Because energy will continue to flow from what to what? From most to least. So energy will flow from most to least until what? What does that mean?
Same on the outside as on the...
So, if the water is reading 35 degrees, then what's the temperature of the block of metal? 35 degrees. And you're 37, so it's going to feel cool to you. Even though a few seconds ago it was very, very hot. Energy is always flowing, always flowing. What happens, what do we say happens when an object, when a heat leaves an object? We say it cools down, but it's wrong, right? It's just all we can really say is that it loses heat. Okay, what do we say about an object when heat enters it? Remember, your body can only sense two things. Heat entering it or heat leaving it. Okay? Now, let me give you an illustration that will help you understand this, and one that you'll never forget. When you're old, you're going, ooh, gross. All right, first period. You come, you get your chair, you put it down, you sit on your chair, and it feels, ooh, nice and cool. I don't like it. So you should start kind of rubbing on it in order to warm it up, right? And pretty soon you don't feel the coolness. Why? The heat from your butt. I call it butt heat. The heat from your butt goes where?
To the chair.
To the chair. And what makes it no longer feel, quote unquote, cold?
Because it's equal.
It is now equal. So now the chair has the same temperature as your butt. Okay? Now here comes the gross part. You go over to second period, and today you sat down, and you, oh, this is nice and warm. Because you were ignorant. Tomorrow you sit down and go, oh, why? If it feels warm, then what's happening? Heat is entering your body. Where did that chair get heat?
From another butt.
From another person's butt.
Oh my God.
So you're sitting there. Now tomorrow, second period, you're going to sit there going, oh, this is just gross. This is just gross. Who sat here? I wonder if you can catch a disease through butt heat.
Can you?
No, you cannot catch it. Microorganisms cannot crawl on heat. Perfectly safe, but it is something. It gives you something to think about, doesn't it? All right. So, hey, you guys are very fortunate because we didn't have plastic chairs when I was a kid. We had metal chairs. And tomorrow you'll learn the concept of specific heat. you'll find out that metal will release and absorb heat very, very quickly. In other words, it didn't take that metal chair was cold in the morning. Didn't take very long to warm it up, but it was cold every period because it didn't matter. Heat enters and leaves metals so quickly that in the 5 or 10 minutes that it took for me to get to my next class, the butt heat would be gone. So thankfully for you, you have to deal with that with butt heat because of the plastic chairs, which have a higher specific heat. We'll talk about specific heat later tomorrow. What do thermometers measure? Heat. Heat, and somebody said it over here. Heat movement. Heat movement. That's really all that it can do. It can measure for you the heat flowing into it or the heat flowing out of it. So if the thermometer little level goes up, if the lever goes up, the level will go up, then heat must be entering it. If it goes down, then heat must be leaving it. Okay, so here they plugged in this little thermometer to water, and there's a bar of steel there, and this is a drill.
Drilling a metal bar causes the temperature of the bar to increase because of frictional heating. The metal bar is placed in water, with a thermometer measuring the temperature of the water. In a short time, the water becomes warmer because heat transfers from the metal bar to the water.
Aha. So what is the thermometer actually measuring? Can't measure the... From where to where? No. Be specific. What is it measuring? Yes, moving from where to where? No. Not from the metal to the water. The water to the thermometer. It is going from the water to the thermometer. Why? Where is the thermometer located? In the water. Okay, where is the heat coming from? Where is the water getting the heat from? The metal. So what you do is you infer that the heat that the water is giving the thermometer must be the heat that the metal gave the water. Very good. All right, so here is, which one of these is your butt? No, second period. Cold, and that's the chair. So
molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
And you no longer feel the chair to be neither hot or cold, right?